give it about 2 more minutes. We always have some late stragglers, so I will start probably around 12:05, just an FYI.
Good.
Hi again. I'm going to go ahead and get started. This is our first Energy Talks of 2018. Woohoo! Thank you all so much for coming. We really appreciate it. My name is Lindsay Peters, and I'm from the Communications Office. Whoa! And also part of the Energy Talks team. Again, we're thrilled to start back with Energy Talks, and we've also decided to do something a little different this year and add some questions to the end, so I certainly hope you take advantage of that. Unfortunately for everyone who is watching on the live stream, we will cut it off before it gets to that point, before opening it up to questions. And just to let you know, in case you missed it, because everything was so last year, just a reminder that Energy Talks is a platform for people to come and learn about what offices have accomplished here at DOE and also what they're working on now. I know I've had people come up to me and said that maybe they didn't even know that the office existed, that they just listened to. So I know that it's been pretty informative as well. If you wanted to rewatch today's presentations or even the Energy Talks from last year, you can watch them on our YouTube channel or on our website, which is energy.gov/energytalks. And we are also recording today's session, so please silence your cell phones. So today we have 3 speakers from across DOE. We have Addison Stark, who's a fellow at Advanced Research Projects Agency Energy, which is known as ARPA-E. We also have Alice Caponiti, who is the Director of Advanced Reactor Technologies from the Office of Nuclear Energy. And we have Alejandro Moreno, who is the Director of the Water Power Technologies Office, also from the Office of Energy Efficiency and Renewable Energy. So we begin today's talk with Addison Stark. Addison serves again as a fellow at ARPA-E, where he has served as acting program director of the Advanced Research and Dry Cooling Program, a thermal engineering program with the goal of reducing the water consumption of power generation. Today, Addison is discussing manufacturing chemistry, rethinking reactor design in the age of advanced manufacturing. And for his fun fact, not to mention the fact that it took him a while to get here yesterday because of the snow, and we're thankful that you made it, but his fun fact is that he grew up on a farm in eastern Iowa. He attended elementary school on Iowa's only island city,
Sabula.
Sabula, thank you, in the middle of the Mississippi River. Given this nautical upbringing, it may come as no surprise that as a current Boston resident, he has taken up sailing and is currently preparing to serve as first mate on the 70-plus hour offshore Marion to Bermuda race from Cape Cod to Bermuda in 2019. Which at this moment, I'm sure you can all agree with the weather we have outside, that a trip to Bermuda on a boat sounds pretty nice right about now.
It's in the summer.
Oh, but even still, just thinking about it. Thank you for joining us today. Addison, please join me in welcoming to the stage.
Thank you. Excellent. I have the clicker. Hi, everyone. As mentioned, I'm Addison Stark. I'm down the hill from ARPA-E. Here we go. And today I'll be talking about something that is really looking forward and talking about how we're extending some of the work we've done in a program like ARID, where we're applying advanced manufacturing techniques to thermal devices for heat exchangers, and looking how we can extend that into the chemical industry. Why are we interested in that? It turns out if you look at a chemical plant today, a large-scale refinery or a gas-to-liquids plant where you're taking natural gas, making liquid fuels or anything else, it is a very large city, and in a lot of ways, to quote a famous quote, a big series of tubes. And in a lot of ways, when you look at this, what this is a one-off prototype design that happens again and again. And we build this large system of pipelines connected to large multi-story reactors, which are also other big pipes. And all of this comes together in a very expensive, capital-intensive way. But why do we do this? You know, what is the big driver for this? Well, it turns out that over the centuries, we've really had a lot of benefit from going to large scale. And we see the reason we do this is because as you increase the plant size, the overall capital cost per size, or the overall amount that you can process, really does increase. So as you go orders of magnitude larger, you do decrease by a commensurate amount the overall cost of that processing. Now, why do we do this? It turns out that if you look at a plant, and as I mentioned, they really are in a lot of ways a series of pipes, the overall cost over the plant size is what we're interested in. How do we decrease that? Well, it turns out the cost is the surface of the reactors, the surface area, and really the plant size, how much you can process, scales is the volume. Well, if we go ahead and do some quick scaling analysis, we can see that the cost over the plant size then looks like the geometric argument of the surface area, the radius times the length, times pi, yada, 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 the volume. Go ahead and simplify this, and we see that the cost scales as a constant over r. So if you make radius really big, the cost should decrease. This is the scaling law that we've used. Everyone, if you're an engineer, learned it in your introductory chemical or mechanical engineering classes. And really, it has given us this law of bigger is better. Immutable in a lot of ways. However, it turns out it's not. If we look at some of the modern work that we've been doing today, and this is data for gas to liquids plants, we're really going off of the predicted scale and the costs of what we expect at these large plants. So, and as the fact that this is a log-log scale, we're not talking just some percentage change off. We're talking factors large. We're talking about billion-dollar cost overruns, which is substantial, and it makes it so it limits what we can do today. So, why does that happen? Let's just take a look at an example. This is from a decade ago. This is a large reactor. This is a sulfur scrubber for a gas processing plant being installed in Kuwait in, I think, 2008. And this is, as we would expect, you know, bigger is better, right? You know, this is very large. There's a very small, relatively small amount of material on the outside for a very big processing inside. But one thing that's not taken into that sort of a cost estimate is the fact that you have a lot of specialized equipment and specialized labor around this. You know, this surface area doesn't take into account these specialized trucks, the people that can operate these, bring these towards the facility, and once you set it up right, also you have other specialized equipment that is really a large capital driver when it comes to the construction approach here, as you then have to set this up, then have to do things like send people up to be able to replace the insulation on the outside that was not there from while it was on the bed of the trucks and things like that. And then when you expand out and look at the plant, you similarly have a multiplication factor of other specialized cranes and equipment for all of these different units, and also large earth moving and other sorts of activities. So these things are not part of this scaling law that we've really followed. So Of course, there are other paradigms that we can follow. So what can we do about this? Well, when we look at another large-scale energy conversion device that we all use, we can really look under the hood of our car and see something that also can be measured in barrels of oil per day and how it, on the scales in which it converts. Turns out if you open an F-150, you can get about a 350 horsepower engine, and that is about a 1 barrel per day conversion device, chemical reactor in a lot of ways. So if you plot this on here, the cost, however, is also off of the projection. And that's for entirely different reasons. We're talking orders of magnitude cheaper, and well, why is that? Is because it turns out we make a lot of them. And if we look at this and we go ahead and say, why is that? Is because as we learn, as we make millions of these a year, we start to benefit not from economies of large scale, but economies of manufacturing scale. And this is the paradigm that not just our office at DOE, but other offices and DOE are exploring and really realizing we can leverage a lot of the tools of manufacturing. What we see is obviously there's a huge amount of economic and technical opportunity in this area under the curve when you rethink moving and building chemical reactors instead of one-off prototype designs to something that might have some sort of a more generalized approach. Examples of what I mean by this are things like the microchannel reactor, and this has been actualized for distributed gas to liquid and biomass to liquid synthesis projects. For example, Velocys is a company active in this, where you're taking the principles of the design of the heat exchanger, which is manufactured on large scales, and putting the chemical reactions within some sort of a framework like that, where you have reactions which have a large heat load, whether it be exothermic where it's rejecting heat or endothermic where it needs the heat. You put it right by the source. So this is one approach. Another thing is to actually look at another thing we had going on in ARPA-E is actually leveraging something that's mass manufactured and converting it for another purpose. So in this case, MIT and the Research Triangle Institute, RTI, had looked at leveraging the internal combustion engine to make a reformer, to be able to convert natural gas to an industrialized commodity chemical syngas, which can be plugged into the chemical industry today. Now, of course, these are both really interesting approaches, but however, some of them are both leveraging designs which had been used for other purposes. So they're not necessarily, the engine has been optimized to deliver torque, to deliver power, and completely convert a fuel to exhaust, which is water and carbon dioxide, to get a complete conversion and get all of the work out of it, not to make chemicals. However, this does show a lot of potential for decrease in capital costs. So my question, or the interest that we've shown here, is how do we, instead of doing this, rethink our approach in general? There are other activities ongoing at DOE that I want to definitely acknowledge because there's exciting work going on. And one of the offices is in EERE in the Advanced Manufacturing Office, where they've partnered with the American Institute of Chemical Engineers to do the RAPID program, which is really focused on these different advanced manufacturing approaches, in particular modular manufacturing, where you can design chemical reactors using traditional approaches, but ultimately make it so they're plug and play. So you can build them at a factory, deliver, and plug them together and be able to do intensified reactors and built and decrease the over on-site capital costs. However, what I want to do is extend this one step further and think about how can we re-engineer chemical reactors from the ground up, really starting from first principles and starting again. And so the vision that I want to give you is this idea of a multi-scale design and manufacturing that we've done before in the information technology, where essentially industry, where industrially this was highly successful to be able to design from the transistor to the microchip all the way to the fully integrated system across multiple scales and thinking about how these interact on all scales and how do you modularly design to play together. The question is, can we do this in the chemical reactor design industry or in that area, from where the chemical reactions occur at the molecular scale through the mesoscales up to the reactor scale? Can we rethink how everything interacts? And so when you look at computationally, how does today computation occur? All of this has been integrated into the idea that you can go buy an off-the-shelf server and put them in a server farm. And some of these might be giving you social media, cat videos, while other things might be doing high performance computing. The thing is, everything is somewhat exchangeable and able to integrate into centralized facilities. And however, today, as we pointed out before, we still have this one-off prototype approach for chemical reactors. The question is, can we replace that and get something that looks more like the computation paradigm today? So what I want to give you is a new paradigm or a new approach where we leverage the tools of advanced manufacturing, additive manufacturing, novel computational design methods, and multi-scale, multi-physics modeling. And so let me give you a little flavor why, or a little highlight of why each of these things I think are critical for chemical reactor design. So let's start at additive manufacturing, which many of us are aware of. You know, it's also known as 3D printing and really comes from also a prototyping approach to be able to create objects. But what it is, it's a layer by layer assembly approach. And really there's been a lot of ongoing activity about being able to build objects with complex geometries, even being able to capture Yoda's hair above his ear. Now this is time lapse, this is not how fast we can do it, but people are working on improving these things to make it more mass manufacturing scalable, working with novel materials. But what it gives us is complex geometries and topologies, connectivities, which are critical for any sort of a flow device. And I'll talk a little bit about that later. And there's a lot of ongoing work in these methods to also work in metal and other sort of high performance materials that are of critical importance to the chemical engineer. So what do I mean by this? If we look at a heat exchanger that's been built by additive manufacturing, this is by Stratasys Systems, direct manufacturing. This is a water heat exchanger. What you're able to do is build a monolithic single build device where everything's interconnected and you don't have to have internal welding and brazing, where you can also have incredibly complex geometries, where you are able to support internal flow structures that otherwise you wouldn't be able to achieve from an extruded device or anything that you've had to weld together. Basically, ultimately, it arrives at a single build, which hopefully, as the materials and the processing improves, allows for higher pressure devices, smaller devices, and other sort of benefits like that. So how do we actually get to the fundamental design, however, is what we really also ongoing work, both DOE, all across DOE, but also in particular in reactive systems, we've seen a lot of advances is in multi-physics, multi-scale modeling. And so these are the computational tools that we want to leverage that represent the physics at every scale. This is an example of looking back at something like we just saw before, a heat exchanger, where you're able to represent the interface of the flows and the fluxes, and to be able to think about how do you optimally either distribute tubes or move beyond tubes altogether, and think about what are truly the optimal internal interfaces and geometries. So if we look at something that's reactive and ask some of the questions, well, how do we design a reactor and really optimally build the optimal structure? This is an example of a pipe reactor, but what this is a gasifier. So we can, all the way down to the details of the fundamental interactions of individual particles, we can get reams and reams of data. And how do we leverage this? All of the data we can get from simulating a reactive environment and start to reconfigure chemical reactors is an exciting thing that's ongoing throughout the department. The last thing, and what I'm really excited about, how do we leverage these tools and look at, you know, if we can build something novel, we can represent the physics ongoing inside of it. How do we design and usually really optimize? So today, if you go out and design things, you can do internal structure, but really, you know, right now today in a series of tubes in that approach, we really say how big do we make it, and then how does the internal flow change, but really we give ourselves one parameter, is just how big do we make it. There are other approaches that we can do, shape optimization. Let's say we add another bend, we go and bulge out a certain side, you know, but this adds a couple more parameters, but you know, a couple of maybe bends and radiuses, but it doesn't give us a lot of extra parameterization. However, if we go ahead and take a from scratch approach and say, we just want a flow in and a flow out and just give us a blank black box, what is the optimal internal structure, we might find that we have internal features and things that we didn't foresee just when we gave ourselves, let us start from the idea that I can just extrude a pipe. What if instead I can build something layer by layer? There might actually be other features that we couldn't access previously. So to give an example of a computational tool like this, there's a topology optimization has been developed over the past 5 decades and really has been used in a lot of structural design, asking the question, using the minimal amount of material, how can I build a structure that actually does what I would hope it would do? So one question you can say is, how do I build a bridge and have it built out of in a cost-effective way? Well, you can start by asking the question, I want to hold, say, X many tons in the middle, how do I do that? Well, you can go ahead and discretize that. You can go ahead and apply this methodology, and just from, without giving any sort of design cue to it, you can quickly returns things like truss structures, things that we do see employed today out in designing of bridges in civil structures. And you can go ahead and apply these types of methodologies to much larger order of magnitude. So recent work has gone into using billions of volume cells to redesign the internal structure of a facsimile of the Boeing wing, and looking at what kind of weight reductions can we achieve if we take really a novel approach at what we get. And actually what has been recently reported is these types of designs actually start to approach the bio-inspired types. You start to see, maybe not biomimicry, but you see these similar structures, and actually they report this looks very similar to the internal structure of birds' beaks. So minimizing weight while maximizing the strength to be able to crack nuts and things like that. You see these similar web structures internally. So what these are really approaching these true optimal designs which just allow structures. Now, we want to extend this also to fluidics. If we want to work in a reactive system, we want to have fluids. So one interesting way where we really start to see interesting emergent behavior, complex design, is if we design a device that, let's say we want to have a passive valve, which makes it easier for fluid to move one way, harder for it to go backwards. So we can go ahead and set up that design problem, and we start to get really interesting internal structures, which, while I might be able to convince you or convince myself that I could have designed a truss and really arrived at trusses, and we have as a people, I think it's much harder for me to convince myself that I could really design this without having seen it. Now, once I see a new heuristic like this, I see a new design like this, I can start to think about how do I apply those principles more generically. And what you see is actually a design like this turns out to have about a 3-fold increase over any sort of the traditional human-designed approaches to do this problem. So what we get, interesting, are these non-intuitive features and key physics that are coming out and represented that we didn't otherwise have in our design. So I want to give you an example of, at ARPA, I was managing our energy water nexus program, ARID, and one of the areas that we used a lot of these tools was in looking at advanced air-cooled heat exchanger design, which is really a cost driver today to move away from water-cooled power plants and move towards air. Is how do you make a cheap enough heat exchanger to reject all of the waste heat to the air? And so one example of a project where we had done this is looking at multi-scale designed additively manufactured heat exchangers. And this was done at the University of Maryland. And this is an example prototype, printed prototype, where the overall structure itself is built out of plastics instead of metal to make it cheaper. But ultimately, you have it connected with highly conductive metal. So these ideas of using multi-materials, complex, developing new printing approaches where you can do an integrated multi-material approach, and then where you can couple the air side with inside the water side while minimizing the overall weight and cost. And the vision is to start with those kinds of leveraging the manufacturing approach, but then looking at how does it scale up to the power plant. So you can think of those as being modules connected to the main flow tubes, and then looking at how does it scale up and being built parallelized into something that can be manufactured at scales that work at large scale energy systems. And so what I want to bring this back to is I'm always excited about new ideas. I know everyone at the Department of Energy is. And so where can leveraging things like additive manufacturing to design a new clicker. We can use new computational methods, really start to look at how do we develop new advanced materials, whether it be composite ceramics with embedded catalysts, novel material, aerogels for separations, or other sorts of really exciting materials, and how do we print those together or additively manufacture those together, and ultimately looking at how can we integrate controls and sensors to think about being able to do a low-cost approach to a highly smart and modular chemical reactor system. And so I want to thank everyone. I will be taking questions, as mentioned before, at the end. And at this point, I'm going to be taking off my mic.
Thank you, Addison. Unfortunately, that clicker seems to have a mind of its own sometimes, but thank you again. And as he said, he will be around after everyone speaks over there to answer some questions for you. So next up, we have Alice Caponiti. She is the Director of Nuclear Energy's Office of Advanced Reactor Technologies, which conducts research and development to reduce long-term technical barriers for advanced nuclear technologies and energy systems. Alice also serves on the Generation International Foreign Policy Group that advises on research and development needed internationally to establish the feasibility and performance capabilities of next-generation nuclear energy systems. As for her fun fact, she mentioned that her closest brush with fame was in 2006 when she literally brushed derrieres with Steve Fawcett, who, in case you weren't sure who that is, he's the first aviator to fly solo around the world. And she did so while exploring the underbelly of the Discovery spaceship at Kennedy Space Center. So that's very cool. Let's please give a warm hand to Alice, who's going to talk to you today about advanced reactors critical for our future energy mix.
Thank you. Thank you. Can you hear me? I think I'm mic'd up. Well, I was excited to be invited to participate in this series because I am an energy enthusiast. And so what I mean by that is at home, we heat our home with biomass. So instead of the electric heat pumps that came with our house, we installed a high-efficiency wood-burning fireplace that heats our home, warm currents of air. I also own 110 solar panels. My husband and I are the do-it-ourselves type, so our first solar project was this 60-panel field array. There were 80 sacks of concrete holding that thing down. And then our second project was a 30-panel roof array. And this coming spring break, we're going to be installing our final 20 solar panels. And with all these electrons that we're producing, I hope to soon, one day, own an all-electric vehicle. So we really enjoy energy, but actually what I'm here to talk to you about today is nuclear energy, and specifically advanced nuclear reactors, and the role that they will play in our future energy mix. So this is our current nuclear landscape. Nuclear energy supplies 20% of our nation's electricity capacity. It represents our largest share of carbon-free baseload energy, 60%. Our 99 existing plants have enjoyed an enormously successful safety record, and they are reliable. These operate 24 hours a day, 7 days a week. They can operate 18 months or more without being shut down for refueling. However, our US nuclear sector is facing an enormously challenged time. We are seeing premature shutdowns of plants because of a very challenging market environment, in part due to the very low cost of natural gas. And we also have a lack of new plants in the pipeline. And so because of these challenges, the Office of Nuclear Energy is working hard to sustain nuclear as part of our energy landscape. And we've got 3 major mission priority areas. The first is to maintain the existing fleet. The second relates to the advanced reactor pipeline. And third is to ensure that we have a robust fuel cycle infrastructure which includes front-end fuel supply as well as back-end fuel management. And today, I'm going to be focusing on this advanced reactor pipeline. And the clicker. There we go. So you might not associate a lot of these words with nuclear. Certainly some of them, like clean, reliable baseload, we do think about with our existing fleet. But some of these concepts, like small modular reactors, microgrids, flexibility, these are the kinds of attributes that we're looking for with advanced reactors that are being designed today. Our current fleet, they're large plants, about 1,000 megawatts on the order of. A lot of our advanced reactor concepts are smaller, ranging from several hundred megawatts to as few as 10 and even single megawatts. They're designed to be scalable plants, transportable, be able to support microgrids. In terms of enhanced safety, a lot of these are being designed for passive safety. So plants that can be operated safely without human intervention or backup electrical supplies to maintain their safety. Some would consider them walk-away safe. So again, our current landscape are large plants providing baseload power to large distributed grid. But in the future, we see nuclear playing an additional role. So in addition to our large plants having smaller advanced reactors, together with fossil and renewable energy sources, not only providing electricity, but also heat for a range of useful energy products. Products such as new chemical processes, clean water, so water desalination and purification, heat for hydrogen production and industrial applications. And so as an example for hydrogen production, we certainly produce hydrogen today, but with the high outlet temperatures of some of the advanced reactors, we could produce hydrogen in a much more economic way. Here we go. So I know you can't read this last chart. Sorry, we've got a lag with the clicker. So I know you can't read this, but what this represents is Third Way, a policy think tank, put together this map to show all of the dozens of nuclear innovators looking to develop and deploy advanced reactors in North America. And to support this industry interest, the Office of Nuclear Energy established the Gateway for Innovation in Nuclear, or GAIN, the GAIN initiative. So in collaboration with the Idaho National Laboratory, GAIN provides the technical, regulatory, and financial resources for a lot of these industry innovators to bring their innovative concepts to market. So one example is GAIN provides a single point of information for the funding opportunities to support these technologies. So as an example, a recently announced $30 million available for cost-shared advanced nuclear energy projects. GAIN also helps connect industry with the national expertise and experimental facilities at our national laboratories and universities. We are also helping with developing advanced computational tools for modeling and simulation to support detailed design and licensing. And we also are helping to supply access to a large amount of data. The Department of Energy and its predecessors developed a lot of nuclear technologies in the past, tested a lot of materials, a lot of fuels, conducted a lot of safety tests. And by making that data available to current designers, it helps them avoid the cost of reproducing that data. So we're working hard to make that data available. So this is an example of a small modular reactor, certainly transportable. This is the new scale small modular reactor design. And so what you see is it is a rather large truck, and that's a rather large piece of equipment, but that's a 50 megawatt power module that can be factory built and then transported to the construction site. So that has the potential to substantially reduce capital construction costs. This is that same module, the 50 megawatts, and that can be packaged together for as many as 12 modules in a single plant. And all of those modules can be monitored and operated from a single control room. So this is a power plant that has a much smaller footprint, a more accessible safety posture, and this NuScale small modular reactor is the first advanced reactor to submit to the Nuclear Regulatory Commission a design certification application for NRC's review and approval. And once approved, this design will be available for national and international customers to proceed with licensing and construction. And so, Department of Energy helped provide a lot of the resources to get NuScale to this point. Sorry. Here we go. Industry is also interested in other advanced reactor concepts that use non-traditional cooling methods because they see the potential for economic benefits, performance benefits. And so these are examples of advanced reactors that are cooled by gas, metal-cooled fast reactors, molten salt reactors. So each of these companies sees a commercial case in these collection of design attributes. And what I didn't mention in the previous map is there's more than $1 billion of private investment behind a lot of these ideas. And so since industry is interested, we're interested. The Office of Nuclear Energy supports a range of research and development to help get these innovative concepts toward commercialization. So we support the qualification of new materials, high temperature materials, materials that can withstand high corrosion, that can be certified for nuclear applications, qualifying new fuels. We're doing a lot with helping to provide the experimental data to validate the models being developed. And these are examples of very small reactors, micro-reactors. And these very small reactors on the order of a couple megawatts, 5 megawatts less, can make a lot of sense for cases where you need energy in remote locations and places where electricity is very expensive. And so these companies are exploring these very small reactors because they see a potential market case. So it could be for remote communities, it could be for defense applications, it could be for emergency response, having mobile, transportable electricity to be able to respond to natural disasters. Third Way developed a number of these graphics to help us visualize what this clean energy might look like in the next 20 years. Transportation is now the largest source of greenhouse gas emissions in the United States. It surpassed electricity production in greenhouse gas emissions. So this is an example of where clean energy, carbon-free energy, can be provided by a small reactor to provide electricity to power electric vehicle charging stations, electric buses that park overnight at a depot and recharge. And the same reactor can also power this electrified commuter train. And, but you can't really see the reactor in this image, but here we can see, here's the reactor and here's the various applications for the electricity that it produces. Industrial processes produce 1/5 of our greenhouse gases in the United States, and this is an important sector. It's an important part of our economy. It employs 10% of our workforce. This is an example where a high temperature reactor producing 700-degree outlet heat can help drive the chemical processing plant, and also can be transported to nearby facilities to use that same heat. So here we see the power source, the heat source, and the applications of that energy. Data servers are an increasingly large part of our energy usage. Currently, more than 70 billion kilowatt hours of electricity per year, and growing. Data centers can require, they need to have reliable energy. It has to be available. This is a scenario where you could have one or multiple small reactors providing whatever the needs are, whether it's 2 megawatts or 200 megawatts. And in this particular scenario, it's coupled with solar panels on the roofs. And these types of reactors can also be sited to expand to support nearby growing communities near some of these data centers. So here we see the various sources of electricity and uses. Remote communities, so Arctic communities like in Alaska, where people are really cut off and depend on very expensive energy. It's expensive to move fuel for generators to these communities. Electricity can cost 16 times as much as the national average and can consume more than half of income of poorer households. And it's kind of hard to see in this image, but this is a residential community here. And while this looks futuristic, this is a real need today. There are communities, Arctic communities, looking for small reactors as small as 2 megawatts because that's enough energy to support residences with up to 1,000 people. And so we've talked about the very remote, the need for transportable power. The other thing that I wanted to cover with you is another very remote application that the Department of Energy provides. That for space exploration. And while NASA is considering reactors for both power on the surface of Mars and on the moon and for propulsion, I'm going to cover a different kind of power source. So not a reactor, but rather, whoops, let me get back. Sorry, there we go. In the upper left-hand corner, this is a radioisotope thermoelectric generator. And this particular model is our most recent design. It produces a little over 100 watts of electricity. And 100 watts does not sound like a lot of energy, but it is enough to power the Curiosity rover on Mars. So this picture is called a hot fit check. This is the first time that a fuel generator was mated with the rover before launch. Testing all the electrical connections, make sure that everything's working. Because once it gets buttoned up into a payload fairing, launched, sent to Mars, it has to work. It has to work when it gets there. And it does. We've had a very successful series of missions with very reliable power at these far destinations. This is a picture of the generator taken by the rover on the surface of Mars. And another mission that I had the pleasure of working on was our first spacecraft to go to Pluto, the New Horizons mission. At the time of launch in 2006, this was the best image that we had of Pluto taken by the Hubble telescope. And in fact, right a couple months before launch, they took one more look at the Pluto system to make sure there weren't going to be any surprises, and they discovered 2 additional moons. So this is how little we knew about the Pluto system prior to sending a spacecraft there. And despite being the fastest thing to leave Earth, a very small spacecraft on our largest launch vehicle, it still took 9.5 years to get there, 4 billion miles away. You need a power source that's going to work. And when we got there, this is what we found, a beautiful, rich planet. And I'm still a Pluto as a planet person. Pluto's still a planet. And what we learned, the suspense with the clicker, is that Pluto is rich with geological features. We can see its atmosphere. So this is an example of discovery in science enabled by reliable nuclear power. So I thank you for your attention, and again, I'll be happy to take any questions after the last talk.
Thank you for speaking to us today and bearing with us with that clicker. Maybe we can get a better one some other time. So lastly, we have Alejandro Moreno, and Alejandro is the director of EERE's Water Power Technologies Office. In this role, he manages efforts to develop and commercialize innovative technologies and market solutions for clean domestic power generation from hydropower and marine energy resources across the United States. And working with DOE's national labs, academia, and industry, the program funds the research, development, and deployment of water power systems through competitively selected cost-shared projects with business, federal, state, and other stakeholder groups. The title of Alejandro's talk today is The Power of Water, New Hydropower Technologies for the 21st Century. And as for his fun fact, his passion for water certainly ventures outside of the workplace, as he used to be a scuba instructor. So very cool. Please join me in welcoming Alejandro to the stage.
Thanks, Lindsay. Indeed, I am Alejandro Moreno. I'm the director of the Water Power Technologies Office. For those of you that might be scratching your heads and wondering what water power is, the Water Power Office manages and implements all of the department's research in both hydropower and marine energy, so energy from waves, tides, ocean currents, which means that we cover two very, very different industries, both the oldest and the newest renewable energy industry, with often very little in common other than the fact that they are powered by water, thus the name of our program. I wanted to say, Alice, I was very impressed with your DIY solar kit, but I noticed you had waterfront property, so I wanted to see if maybe we could get you to install a tidal turbine.
I'm happy to be a tester.
Okay, I'm going to hold my breath while I use this clicker here. All right, twice seems to be the charm. So as I said, and all of you probably know, hydropower is the oldest renewable energy technology. It's actually the oldest electricity generation technology. It's the largest renewable energy technology in the US. Anybody here know when the first hydroelectricity project or power was first generated from hydroelectricity? My hydro team doesn't get the answer, but I bet they don't know. 1878 in a house in England, and it was to power one arc light in one gallery. So in an art gallery. So if there are any analysts here, I'd like to see the LCOE analysis of that, please. But today there are 2,000 hydroelectric plants in the United States. They provide about half of the country's renewable energy, 7% of the country's electricity, roughly about the same as wind. Hydro has a greater capacity, about 80 gigawatts, and wind has a greater capacity. Hydro puts more electrons on the grid today, but that may change. And hydro is also tremendously valuable. Again, this is probably not news to a lot of people, but provides over 87,000 jobs across 49 states. There's only one state in the US that doesn't have hydropower. It's also very inexpensive. It's one of the least expensive sources of electricity in the US. The very, very cheap retail power prices that you see in the Pacific Northwest, 2 to 3 cents a kilowatt hour, primarily driven by federal hydropower assets. And over 90% of all hydropower projects provide non-energy benefits, things like navigation, flood control, water supply, irrigation water. I can't blame that on the clicker. But what you might not know is that hydropower is exceedingly important to the grid. What you see here is an analysis done by PJM, so the grid operator for our area, for the Mid-Atlantic, that went through and looked at every single one of the technologies in their generation portfolio and evaluated their ability to contribute to the reliability and the resiliency of the grid. And hydropower came out on top, above even natural gas and coal, which you see here, which both provide quite a lot of these attributes. And this makes sense because hydropower can react as quickly as a battery can in sometimes to the sub-second range, but certainly in the second range. It has a tremendous amount of inertia with the rotating mass, but provides, because you have water in a reservoir behind your dam, almost perfect flexibility and dispatchability. So we can provide really every service that the grid needs from inertia, black start capacity, to primary frequency response, secondary frequency response, all the way up to hours and days of load following and balancing. And when you put pumped storage hydropower into the mix, which you see in the upper right here, that ability of hydropower is increased, doubled or exponentially, because pumped storage hydro can provide all of those same grid services, not only while it's injecting power into the grid, but also while it's taking power out. And of course, on top of that, can provide long-term bulk storage. It represents about 97% of the storage on the grid today. One thing I do want to point out here, and all of my colleagues in the hydropower industry would be angry at me if I didn't, this graph is almost always shown in log form. If you show it in non-log form, it looks like this. I can't imagine why nobody ever shows it this way. So what does this mean, practically speaking? Well, I used to work at the World Bank. I was there in their energy practice for a number of years. And one of the primary goals that we have is increasing the utilization of renewable energy in the power sectors in developing countries. And when countries, for example, like Costa Rica or like Portugal, succeed in generating or using renewable energy exclusively or predominantly for a long period of time, we really take notice. And it's something that an increasing number of countries are doing. And you see here, Costa Rica ran on renewables for 300 days last year, including about 70 days straight. Portugal for a shorter number of time, but still being able to run a grid without without lots of imports exclusively on renewables is very different than just having a high level of renewable capacity. And what we found is almost always these are on the backs of hydropower. So in Costa Rica, it's easy. You've got 78% hydropower. You don't necessarily need that much. Portugal has about 30% of its power generation mix is hydro, and that allows the flexibility to balance the variability of wind and solar and other renewables. And for this reason, you see quite a lot of hydropower still being developed. In 2016 alone, 30 gigawatts, including 6 gigawatts of pumped storage. You're seeing new pumped storage projects come in pretty unexpected places. Saudi Arabia and Egypt both have multi-gigawatt pumped storage projects in the works. That's to balance their very ambitious solar energy targets in both countries. And even China is looking to double its current pumped storage capacity to reach 40 gigawatts by 2020. So obviously most of those projects are well underway. So what does that mean for us? You may ask, well, hydropower is clearly very valuable, but it's all built out in the US and it's completely understood, right? And I would say, well, I'm glad you asked. That's a great question. While hydropower can provide all these values, most hydropower was not designed to operate at that level of flexibility over a long period of time and to that extent. And what you see here on the bottom is a graph showing the ramping. Effectively, this is the power output over time for a particular plant in Missouri right before and right after the MISO, the Mid-Continent Interconnect Ancillary Services Market went in. And you see it went from ramping up and down about a dozen times in a 10-day period to ramping up and down about 40 times in that same period. And this is for a plant that was originally designed as a peaker. Many plants just operate flat like this. The reason for that being most hydropower turbines, and the problem associated with this, are designed to operate at one single maximum efficiency. And when you operate below that efficiency, as you see in the upper right, you get these little mountains of stress, which is exactly what these are. These are a measure of the stress on the turbine itself as you come down in power. And what you see here, you are operating in these lower power ranges far more often when you're operating flexibly and you're designed to integrate variable renewables or to provide reliability services to the grid as is increasingly needed. And so what do you see? The potential that O&M costs get much higher. And here you see with a certain amount of data we have, it's not the entire fleet, we are seeing O&M costs continue to increase. We're seeing availability and also efficiency of plants going down. What we don't have is the exact driver. So we don't know exactly what parts are failing and how often. That's part of the work that we at DOE are doing. We've collected the largest data set for the hydropower fleet in the country, the only one that really covers almost every single plant, both at the plant level and at the unit level. But what we see undoubtedly is that hydro does need to change the way it's designed and operated to meet the needs of the 21st century grid. But if it does that, the value proposition is quite high. And you see here a very preliminary result, so I want to stress that. But this is from the North American Renewable Integration Study that NREL is leading. And they ran a sensitivity analysis where they used software that allowed for the full flexibility of hydropower in the Pacific Northwest and southwestern Canada. And what you saw was almost a 2% savings in total system costs compared to hydropower running nearly flat with the original software that they were using, which just didn't have the modeling capacity to really account for the full flexibility. And you saw costs of the price coming down from $38 a megawatt hour to 27. So significant value. What you'll also see is pump storage technologies evolving. This is on the theme of small modular units. This presentation or this energy talk seems to be weaving together. This is an example of a collaboration we have with Shell Energy looking at a 5 megawatt pump storage plant using a floating membrane as the upper reservoir. Another fairly common technology paradigm that we're seeing now is pump storage using seawater as the lower reservoir. And this is what the Egypt and Saudi Arabia plants I was talking about are using. This is actually a diagram of a plant in Chile. Right now, using best available materials, however, these projects cost about 30% more than a standard pump storage plant because of the corrosion. Working on materials that can reduce those costs is another potential critical research area. If we can get that right, it dramatically expands the geographic opportunities for pump storage, both in the US and across the world. I'm not going to even dare to go back. Lastly, on small hydropower, I would be remiss to not talk about that because there is a conception that hydropower is built out in the US, and that's far from the case. Right now, small hydropower accounts for 1,700 of the 2,000 plants in the US, so the vast majority of plants. Obviously, it's a relatively small percentage of generation, but it's still more generation than landfill gas, geothermal, and small PV combined. So it's not small. But as we saw in the 2016 Hydropower Vision report that DOE released, there's still upwards of about 30 gigawatts of potential of small hydro, both in new streams, but also in putting powerhouses in current dams that are not powered. Of the 80,000 dams in the US, only 2,000 have power in them. The vast majority aren't good candidates for powerhouses, but plenty are. And here you see an assessment we've done of the non-powered dam potential in the US. But in order for this to be developed, the slide needs to change. Nothing. Yeah. Hydropower needs to be cheaper. It needs to be easier to install. It needs to continue to make strides in being environmentally friendly. And it needs to be able to provide those same grid services we were just talking about. And on the left, you see a diagram from one of the key research projects we have that's looking to adopt a modular, standardized approach to small hydropower. This would be a massive paradigm shift for hydro right now, where every single plant and every single turbine is custom designed for the site. It makes sense for a lot of large plants where small increases in efficiency make a big difference over the long run in revenue. For small sites, much less so, and where you really need to focus is manufacturability, looking at some of the advanced manufacturing techniques that Addison talked about and how that can be adopted into or adapted for some of the customized shapes that you wouldn't necessarily get with traditional manufacturing techniques is also a key avenue of research. And on the right, you see a graph and a photo from a project that we're working on with Idaho National Lab to develop control systems that allow the integration of multiple small hydro projects right now that don't have the reservoir capacity and the ability to provide some of those grid services I was talking about. Well, if you link them together with small amounts of batteries, all of a sudden you have that ability. And we're starting to pilot that on a project with DOE's Grid Modernization Initiative in a city in Alaska, Cordova, Alaska, as part of the mini grid that they have operating there. We call it a mini grid, they call it their utility system. And lastly, the elephant in the room often with hydropower is its environmental impact. Hydropower has made tremendous strides over the last 50 years. Many, many projects right now have negligible or very little or negligible environmental impacts, but there's always work to be done to improve. What you see here on the left is a device that was developed in partnership with DOE. It's a tube that allows much safer and more cost-effective passage of fish, both upstream and downstream from dams. It is affectionately known as the salmon cannon. Despite the name, it has gotten to the point where the regulators actually are very supportive of it. This was adopting a technology that was first used in fruit picking and transport. And if you can imagine picking fruit like peaches that are extremely soft, you need to do it very quickly, but you need to do it without putting any blemish on the fruit whatsoever. Same idea with fish. But what you also see on the right is new practices and technologies that allow selective water withdrawal from reservoirs. What this means is technologies can be used not only to mitigate the environmental impacts of hydro, but to allow hydropower to provide environmental benefits. Technology here, you can choose the temperature of the water by choosing where in the reservoir you withdraw from to manually control the downstream temperature. As we know, if there are any climate scientists in the room, downstream temperature is one of the issues that people are most worried about, one of the largest potential ecosystem issues in riverine systems right now. This allows us a mechanism to actually help control that proactively. So I'll end with a beautiful image of hydropower. This is how we view it, and if we have time for any Q&As, we're happy to take them now. I know we're running a little over.
Yes, thank you so much, Alejandro, and thanks everyone for sticking around. We have run a little bit late, but I do want to leave some time for some questions, take advantage of having them here if you have anything you'd like to ask. But before we move to that, I want to say goodbye to everyone who is watching on the live stream, and also let people know what we do have lined up for February 15th, which will be our next energy talks. We do have 2 people, as you can see, those who we have for February 15th, and we're still working on a 3rd. As always, if you know of someone who you would like to nominate to participate in this program, we're happy to hear who you have in mind and see if we can work it out. So with that, thank you so much, everybody watching, and I'll open it up to some questions. If anyone has a question for Alejandro or Addison or Alice, feel free to raise your hand and we'll get that answered.